So good afternoon, everybody. Title of my talk is Dense Baryonic Matter in Light of Nuclear Saturation Properties and Astrophysical Observables. In this work, my collaborator is my PhD student, Vivek Barua Thapa. So, the unique laboratory in the universe for dense baryonic matter is astrophysical compact object neutron star. Neutron stars are the stellar remnant of massive stars, ending their lives by supernova explosion. Due to their high mass, the massive stars ends their life after reaching the most stable element, iron. Then the iron core collapses due to the immense gravity, and the outer layer blow off in supernova explosion. And the core collapses either into a neutron star or into a black hole, depending on the mass of the progenitor star. Sorry. Now, inside the collapsed core, according to Barry and Zwick's proposition, the electrons are pushed into the nuclei. And inside the nuclei, electrons combine with the protons and produce neutrons. So the nuclei become neutron rich. Thus, and with the increase in density, when density reaches about of the order of 10 to the power 11 gram per cc, the neutrons drip out of the neutron rich nuclei. Thus, the matter inside the collapsed core is composed of free neutrons with small admixture of protons and electrons to maintain the beta equilibrium and charge neutrality of the matter. Then the neutron degeneracy pressure balances the inward gravitational pull and form the neutron star. The average density of matter inside the neutron star is a few times of the normal nuclear matter density. So inside the neutron star, the density increases gradually from surface to center. In the outer crust, the density starts from around 10 to the power 6 gram per cc and gradually increases with the increasing distance from the surface. At the surface, the matter is composed of iron nuclei arranged in lattice and immersed in degenerate gas of electrons. With the increase of density and the distance from the surface, the electrons are pushed into the nuclei. The Fermi energy of electrons inside the nuclei is so high that inverse beta decay occurs inside the nuclei and neutrons are produced. So, inside the nuclei, neutrons become degenerate, and around density of the order 10 to the power 11 gram per cc, the highest energy of neutrons inside the nuclei exceed the binding energy. Consequently, the neutrons become free of the nuclei and drip out of nuclei. This ends the outer crust, and the inner crust consequently starts at the density of 10 to the power 11 gram per cc. So the inner crust is composed of neutron-rich nuclei, free neutrons and electrons. The density again increases with the distance from surface, resulting smaller and smaller nuclei, and ultimately at around density 10 to the power 14 gram per cc, the nuclei merge together, reaching core. The core is thus composed of free neutrons with small admixture of protons and electrons to maintain the beta equilibrium and charge neutrality of the matter. And sometimes other electrons, heavier electrons, muons also appear inside the neutron star matter. But density goes on increasing towards the center. So at the innermost core of the neutron star, the density is so high that the composition and properties of matter remains uncertain. At when density is above nuclear saturation density or even larger than the 2 times nuclear saturation density, the particle energies are so high that some exotic particles, that means heavier strange and non-strange baryons, may appear. However, the matter properties at that much high density are not well understood. At that much density means supernuclear density, because of the difficulty to produce such matter in terrestrial laboratories. So only way to understand the dense matter from the laboratory experiment is to extrapolate the nuclear matter properties at nuclear saturation density. And then verify the model from the astrophysical observations from neutron stars, as neutron stars are the only laboratory to produce highly dense matter. Among many other models, there are many models for highly dense matter inside the neutron stars. Among those models, the simplest and mostly widely used model, phenomenological model, is covariant density functional model. This is the Lagrangian density for that model. In this model, the baryons interact among themselves via measure interactions. The mediator measures in this model we consider as isoscalar scalar meson, sigma and sigma star, isoscalar vector meson omega and phi, and isovector vector meson rho. The estimate of the baryon meson interaction is inferred here by the values of this coupling parameter G, and the coupling parameters are inferred from the nuclear saturation, applying this model to the matter at nuclear saturation density. From this model, to reproduce the compressibility of matter at nuclear saturation density, either the nonlinear self-interaction of the isoscalar scalar meson sigma should be incorporated, or the coupling interaction between baryons and mesons should be considered as density dependent. So if the nonlinear interaction of sigma and sigma mesons are considered, then it is known as nonlinear model, or in short NL model. And if the density dependence of these coupling parameters are considered, then the model is known as the density dependent model, or DD model in short. Now, as already I have mentioned, that one way to understand the dense matter is to extrapolate the nuclear matter properties at nuclear saturation density. And the dense matter inside the neutron star is highly asymmetric. So the symmetry energy of nuclear matter and its behavior with density play a crucial role to determine the matter properties inside the neutron star. However, unless very recent estimate of symmetry energy ESIM and its slope with density LSIM by the nuclear experimental data PREX2, the nuclear symmetry energy is not well constrained by nuclear data. So here in these two figures, we show the so far known range of ESIM and LSIM at nuclear saturation density by this red vertical double arrow. And this black double arrow here shows, in these two figures, shows the recently obtained range of ESIM and LSIM at nuclear saturation density. So first we compare the so far existing equation of states models with the so far known range of ESIM and LSIM. So we see that the so far the existing equation of state parameterizations are furnished in such a way that they can reproduce the so far known range of ESIM at nuclear saturation density. However, with the so far range of LC, we see that the nonlinear parameterizations cannot reproduce the so far known range of LCM with these parameterizations. So we try to tune the parameterization of the equation of state to satisfy the recently obtained range of ECM and LC at nuclear saturation density. So in that Lagrangian density, what I have shown just now, the coupling of nucleons with isobacter vector meson rho is important for the isotopic asymmetric nature of the matter. So the choice of G rho n, the coupling between baryons and the isobacter rho mesons, isobacter vector meson rho, determines the relative abundances of protons and neutrons and also the symmetric energy of the matter at saturation density. So here, and to get the specific density dependence of ECM, that is the LC, what is recently obtained from Prex2 data, the coupling between baryon and isobacter vector meson rho should be density dependent, and so we have taken G rho B as density dependent even in the nonlinear parameterizations with the function like this. Here n is the matter density, n0 is nuclear saturation density, so G rho n at n0 and a rho are the two model parameters for this density dependence of the coupling G rho n. So with this kind of density dependent, we have tuned the parameters to get the recently obtained range of ECM at nuclear saturation density with the values of LCM, which is within the range of recently obtained values from Prex2 data. Now, another constant obtained from recent neutron star observables and heavy ion collision experiment is the range of ECM at 2 times nuclear saturation density, which is shown by the black particle line here. And so we see that from this condition at 2 times nuclear saturation density, the maximum permissible value of LCM is 85 MeV, which lie within the recently obtained range of LCM. And for this, and for obtaining this experimentally obtained range of ECM and LCM, the variation of G rho n with density is shown here. For in the upper panel, we have shown for DDMEX parameterizations, and for in lower panel, we have shown for GM1 parameterization in nonlinear scheme. So in this tuning of the parameters, for other parameters of the model, we stick to the original parameterizations of DDMEX and GM1 respectively. And the parameter G, we have two parameters of the density dependence function, G rho n at n0 and a rho. This parameter, the G rho n at n0, determines the value of ECM at nuclear saturation density. So within the experimentally range of ECM, we plot the variation of this parameter of G rho n n0 with the values of ECM in this figure. Similarly, the parameter a rho determines the density variation of ECM, that is the LCM. Hence, this figure shows the variation of the parameter a rho with the values of LC. and we have taken that range of the LC within the experimentally obtained range of LC. Now, it is very natural that the values of LC for the matter determines the particle abundances of the dense matter. So in the upper panel, we show the particle abundances for dense matter for original DDMEX parameterizations, which reproduce the value of LCM to be 49.57 MeV. And in the lower panel, we show the same thing, but with LCM is equal to 85 MeV. So we see that with increasing value of LCM, the delta minus appear later. Consequently, to maintain the charge neutrality, lepton population decreases slowly compared to the original DDMEX parameterizations. And because of the later appearance of delta minus, hyperons appear comparatively earlier. As with increase of LCM, the appearance of delta occurs later. The increase in LCM stiffens the matter. And this is evident from these figures also. These figures shows the variation of pressure with number density. So we see that, and the matter pressure range at 2 times nuclear saturation density has been obtained from recent observation of GW 170817, and this is shown by this yellow vertical line. So we see that with the newly obtained range of LCM, with LCM, all the parameterizations satisfy this constant from GW 170817 observation. Even the pure nucleonic matter and the matter composed of hyperons and delta, they both satisfy the constant. And we also see that when inclusion of delta variance softens the matter, and so in case delta admixed baryonic matter, this condition helps to constrain the meson delta attractive potential, as larger attractive potential softens the matter. So that means that from DDMEX parameterizations, we see that the maximum admissible value of R sigma delta, that is the ratio of meson delta coupling to the meson nucleonic coupling, is 1.3. Now, as expected, with nonlinear parameterizations, the inclusion of heavier variance softens the matter, and so the mass radius relation satisfies marginally the lower bound of maximum mass of neutron stars. That means that nonlinear parameterizations do not go with the astrophysical observations for delta admixed matter inside the neutron star. And the variation of LCM has little effect on the maximum mass. However, it affects the radius of intermediate mass stars. Intermediate mass stars means the radius of star with mass around 1.4 solar mass. We see that the pure nucleonic matter with both the parameterizations are too still to satisfy the radius constant for the intermediate mass star. So from this observation, we can conclude that the matter within the compact object, within the compact stars, only pure nucleonic matter is not possible. Only delta admixed hyperonic matter is possible with density dependent parameterizations. Now we examine the condition of matter obtained from GW observations. Here in this plot, we show the in plane of lambda1, lambda2, the tidal deformability of the two participant stars in the binary merger events, lambda1, lambda2. We can plot the contour of lambda tilde. The lambda tilde means the mutual tidal deformability, and the maximum value of lambda tilde, which is obtained from these observations, has been estimated by two calculations, and the magnitude of these two calculation gives either maximum lambda tilde is 900 or 720. So in this plot, in this lambda1, lambda2 plane, the colored region shows the allowed region for lambda1, lambda2, which is compatible with the maximum possible value of lambda tilde, 900 or 720. So from the figure, it is evident that if we consider the softest delta admixed matter with R sigma delta 1.3, the orange curves, then they lie in the allowed region. However, with less attractive potential, that means with R sigma delta is equal to 1.1, the red curves, only with LCM is equal to 106 MeV, the observational limit on lambda tilde is not satisfied. So what we have already seen that with LCM up to 85 MeV, all the astrophysical observations and nuclear physical experimental data are satisfied by the matter. And with pure nucleonic matter, the contour does not lie within the allowed region for any parameterizations. So these observations strengthen the idea of exotic matter appearance at highly dense matter. From this constant also, we can understand the matter properties. From the GW observations of binary neutron star mergers, the range of tidal deformability lambda for 1.4 solar mass star has been estimated, which is shown here by the red and green vertical lines. These two lines are for two different estimates. So here also we see that the pure nucleonic matter is too stiff to satisfy this constraint, this condition, but the matter with delta admixed hyperons satisfy both the constant. Hence this constant also strengthens the idea of delta appearance within the compact stars. Now we plot the tidal deformability of 1.4 solar mass stars with the values of LCM for different parameterizations GM1 and DMEX, and for different compositions. One composition is pure nucleonic matter, and another composition is with delta admixed hyperon matter. So we see that, and the red horizontal lines show the maximum limit of lambda 1.4 from two different estimates. So we see that this green curve, that the pure nucleonic matter case with nonlinear with density dependent parameterizations is too steep to satisfy the maximum limit of lambda 1.4, but with nonlinear parameterizations it satisfies the lambda 1.4 limit of 800 within the limit of LCM 100 MeV. And matter with hyperons and delta variance satisfy both the estimate with maximum limit of LCM 95 MeV for the density dependent parameterizations, and for the entire experimentally obtained range of HC for nonlinear parameterizations. So, and we note that if we plot the values of lambda 1.4 with LSIM. So there is a tight correlation with of lambda 1.4 with LSIM for a specific parameterization and composition. So we can estimate the compactness of the 1.4 solar mass star for different values of LSIM with different compositions and parameterizations. They also show good fit with single parameterizations and specific compositions. So from this plot, we can understand the lower bound. We can estimate the lower bound of compactness of the 1.4 solar mass star, which is around 1.16. So, in summary, we can estimate the we have the estimate of nuclear symmetry energy and its density variation with LC. And with these new results, the new parameterizations of the equation of state for highly dense matter inside the neutron star is necessary. And from this, we can narrow down the range of LC from astrophysical observations. So we obtained, already I have shown that the lower limit of LSIM is around 50 MeV and the upper limit is around 85 MeV. With this range of LSIM, the equation of state for pure nucleic matter is too stiff to satisfy many astrophysical observations that we have observed. And this puzzle can be solved with the possibility of appearance of exotic matter at high density inside the neutron stars, such as hyperons and delta baryons. And the newly obtained range of LC also helped to get the idea of interaction potential of delta baryons with the mesons. Thank you.